Hey guys, it's Mrs. Rooker. I'm going to be doing day 1 of probability with you guys. And I'm just going to start with the definitions that I have already up here for you. So make sure to write this down. The definition of permutation is the act of arranging objects or numbers in order. So the big kind of key word here is order. When we talk permutation, order matters. Later on, we are going to talk about combinations, and in combinations, order does not matter. So permutations are about order. So yeah, make sure you have that one written down. And then factorial is a term that you're going to need to know for today. And a factorial is the product of an integer and all the integers below it. And it's notated a specific way. Kind of fun, actually. Like an example is 4 factorial is written like this. It's 4 with an exclamation point after a word. And what it means is 4 times 3 times 2 times 1. Which really you don't need that 1 because multiplying by 1 just keeps it the same. So 4 times 3 is 12 times 2 is 24 times 1 is also 24. So 4 factorial would be 24. All right, so go ahead and pause the video if you need to continue writing that down, and if you're done, then we will move on to the fundamental counting principle. So, fundamental counting principle, if Mr. Sullivan has 4 suits, 3 shirts, 2 ties, and 2 ties, how many different outfit combinations can Mr. Sullivan create, given that he can choose 1 suit, 1 shirt, and 1 tie? Draw a tree diagram that illustrates this. So we are going to first draw a tree diagram, and then we can talk about how to do this without a tree diagram. So the way this tree diagram is going to look, and I used to actually draw the shirts and draw the ties and all that, but it's a lot easier to just write S's or T's. So I'm going to put first suits. I'm going to put that he has 4 suits. 1, 2, 3, 4 suits. And he has 3 shirts. I'm going to call his shirts, I'm going to call them blouses so that we have a different letter that goes with this. So we'll call his shirts blouses so we can put B. So let's say he wore the first shirt. He has the option to choose between 3 different blouses. Sorry, if he wears the first suit, he has the option to choose between the 3 different blouses that go with that suit. So same thing if he chooses the second suit. He has 3 different shirts he could wear with that one. Same with the third suit. And same with the 4th suit. And then from there, he has the option of 2 different ties. So if he wears the first suit with the first shirt, he still has the option between 2 different ties. Then if he wears the first suit with the second shirt, he still has the option between 2 different ties. So we're just going to put 2 ties off of each of these blouses or shirts, whatever we want to call them. Probably shouldn't call them blouses. He probably wouldn't like that, but that's okay. So 2 ties off of each shirt. It's a little tedious drawing these tree diagrams. You might remember these from geometry. Actually, I think we stopped this in geometry before you guys got there. All right, now based on this tree diagram, what we can do is we can add up all of these T's. So all of the bottoms of the trees, all of the, I guess the leaves, we can add together. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That means there are 24 outfits that he could create, assuming that all of his clothes match. there's an easier, quicker way to do this than just drawing the tree diagram. And what you can do is something called the fundamental counting principle. And that means you are going to multiply together the 4 suits times the 3 shirts times the 2 ties. 4 times 3 is 12, times 2 is 24, and that gives us our 24 options. So we just multiply together the amount of options that we have. So by using the diagram, we can see that an easier way to do this would be multiplying. This is the fundamental counting principle. So we're going to use that on a bunch of other little example problems. If you want, you can pause the video and try some of these on your own, or you can just watch me. You're buying a pizza. You have a choice of 3 crusts, 4 cheeses, 5 toppings, and 8 vegetable toppings. Sorry, 5 meat toppings, 8 vegetable toppings. How many different pizzas with 1 crust, 1 cheese, 1 meat, and 1 vegetable can you choose? So assuming that you are getting 1 of each of those things, we can use the fundamental counting principle. And we can just take 3 times 4 times 5 times 8. 3 times 4 is 12, times 5 is 60, times 8 would be 480, I believe. All right, and then the next one, how many different pizzas could you choose if crust is not an option? So it's worded a little weird, but meaning if you can't choose your crust. So if you can't choose your crust, there were 3 different options for crust. If you can't choose that, we're just going to take away the 3. So we're just going to do 4 times 5 times 8. Or we could just divide that by 3. 4 times 5 is 20, times 8 is 160. Which is what we would have gotten if we had just divided the 480 by 3. All right. Moving on, a town has telephone numbers that all begin with 329 followed by 4 digits. How many different phone numbers are possible if numbers can be repeated? All right, so if numbers can be repeated, we know that they're going to start with 329, and we don't know what the other 4 digits are going to be. But it could be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, which leaves us, that's 10 options right there. So there's 10 different options for this digit. If numbers are being repeated, then there could be 10 different options for the second one as well. 10 different options here, 10 different options here. So we have 10 times itself 4 times 10 for the fundamental counting principle gives us 10 to the 4th power, or we could write that as 10,000 different options for phone numbers if the digits can be repeated. All right, if the digits cannot be repeated, so the next part, 329, and we don't know the other 4, there's going to be 10 options for the first one. But if you're not allowed to repeat whatever number goes there in that first digit, then there are now only 9 options left. And then if you're not allowed to repeat those 2, there are now only 8 options left. And then if you're not allowed to repeat those 3, there's now only 7 options left. So we're going to be doing 10 times 9 times 8 times 7, which I'm going to need a calculator for. 10 times 9 times 8 times 7, 10 times 9 times 8 times 7 is 5,040. So significantly fewer options if you're not allowed to repeat those digits. All right, option C, how many different 7-digit phone numbers are possible if all the digits can be repeated? So 7-digit phone numbers. So now we're saying that we don't need 329 to start. So no more 329. It's going to start with whatever we want it to start with. So there are 10 options for this first digit. And then, I mean, this is important. It says numbers can be repeated. So there's still 10 options for the second digit, and 10 for the third, 10 for the fourth, 10 for the fifth, 10 for the sixth, 10 for the seventh. So I just do 10 times itself 7 times, which is going to be 10 to the 7th power, which is a 1 with 7 zeros behind it. 1, 2, 3, 4, 5, 6, 7. Should be 10 million different possible phone numbers if numbers can't be repeated. All right? And there would be significantly fewer if numbers could not be repeated. Okay, number 3. 8 baseball teams are in a league. How many different ways can teams finish the season? So, I like visuals, so I kind of drew out, like this here is first place, second place, third place, fourth place, fifth place, sixth place, seventh place, and 8th place for the season. So, since there are 8 teams, there are 8 possible different teams that could get first place. Now, depending on which team gets first place, that team is not also going to get second place. So, whatever team gets first place is now out of the running for getting second place. So there's only 7 teams that could have gotten second place. And there's only 6 teams that could get third place, 5 teams remaining for fourth place, 4 teams, 3 teams, 2 teams. And once 1st through 7th are taken, there's only 1 team remaining that can get 8th place. So really what we have here is 8 factorial, because the fundamental counting principle says that we're going to multiply each of these numbers by each other. So we're going to multiply 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is just a fancy way of saying it's just a long way of saying 8 factorial. So let's multiply those. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I got 40,320. Go ahead and check my math in case I did something wrong. All right, option B, how many different ways can 3 of the baseball teams finish first, second, and third? So now we don't care about the people later in the game or further down in the standings. We just care about the first 3. So how many different ways can they finish first, second, or third? So there's still 8 teams in the league. So there's 8 teams that could get first place. There's 7 teams that could get second place. And there's 6 teams that could get third place. Because whoever got first place isn't still in the running for second or third, and so on. So I'm just going to do 8 times 7 times 6. 8 times 7 times 6 is 336. Different ways can teams finish if there are only 6 teams competing. So if we're talking about finish completely, I think we're talking more along the lines of like the first problem. 1, 2, 3. We don't care about just first through third. We care about all the places. So we'll put... and now there are 6 different options of teams who could get first place. And then the one who got first place is no longer in the running, so we don't count them, and we don't count the first 2 now. Now we don't count the first 3, so now we're down to 3, then 2, then 1. So now we're just doing 6 factorial. So we'll do 6 times 5 times 4 times 3 times 2 times 1. And I got 720. So it's interesting that just 2 fewer teams than what we had up here, and we have a lot fewer options for how they can place. So we can actually use a little formula for permutations that will kind of help us out with those problems that we did above. The number of permutations of R objects from a group of n distinct subjects is denoted by, and it's these little subscripts. So it's a subscript n, p, and then a subscript r. And the formula is n factorial over n minus r factorial. where, remember, factorial means you multiply the integer by all the integers below it. So n is always going to be the whole group, and r is going to be a subset of the group, so the smaller group. All right, Riley has 6 young ladies that would like to take him on a date. However, due to his dedication to algebra, he only has 4 free nights this week. How many different orders can he go out with the ladies? There's 2 kind of ways that we can do this. One way is we can think about the fact that he has 4 free nights. So 1, 2, 3, 4 free nights. On the first night, he has 6 options of ladies that he can take on a date. On the second night, and we're assuming here that he's not repeating dates with the same person, so sounds really, really bad. On the second night, he now has 5 options of ladies that he could take. On the third night, since he's already gone out with 2 of them, he has 4 options left, and then on the fourth night, he has 3 options left. So we're basically just going to do 6 times 5 times 4 times 3, which I believe I did this a minute ago, 360. So that's one option for how we can do this. Or we can look at the formula for permutation. So this is P. Oops. What we have here is the total number of ladies is 6, and the total number of nights is 4. So we use this formula. 6 factorial divided by 6 minus 4 factorial. So 6 minus 4 factorial, which just means 6 factorial over 2 factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1 over 2 factorial is 2 times 1. Well, what happens here is the 2 and the 1 cancel, and we're left with just 6 times 5 times 4 times 3, which is exactly what we had in the beginning. So this formula is, if you kind of forget how to do this, you can use the formula, but it works the same way as our other option. All right, Audrey has 9 chores to complete, and how many different ways can she complete 5 of them? So she's only doing 5 of her chores. 1, 2, 3, 4, 5. She has 9 options for the first chore she does. After she's done that chore, she only has 8 options for the second chore she does, and then 7 options for the third, 6 for the fourth, and 5 for the last chore that she does. Multiply those all together. 9 times 8 times 7 times 6 times 5. I got 15,120. Now, we could get the same thing if we treated this like a permutation here. Our n is going to be 9, and then our subset is 5. So this can be 9 factorial over 9 minus 5 factorial. So 9 minus 5 is 4 factorial. So this will be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. These all cancel, and we're left with the same thing that we had using our first method. Last section is talking about permutations with repetition. Usually when we're talking about this, we're talking about rearranging the letters of a word when some of the letters are already repeated. So the number of distinguishable permutations of n objects, where n is the number, where one object is repeated s sub 1 times, and another is repeated s sub 2 times, and so on, is this. This little box is just supposed to be a multiplication symbol, so don't really worry about that box. It's just we're multiplying together everything that's on the bottom. So this sounds a little weird, but if you look here, we're trying to see how many times we can rearrange the letters in the word even. But the issue is we have two E's. So these are not distinguishable. So we don't want to count those as two different options, because if we move those, if we switch the E's, you can't even tell we switched them. So instead of saying that this would be, since there's 4 of them, we can't just call it, 4 factorial, because one of the numbers has already repeated. So what we do is we do 4 factorial, because there's 4 letters in here. That's what this on top is 4 factorial. And then we divide by the number of times each number is repeated. So we have E repeated twice, and we do that factorial. That's the only number that's repeated twice, so that's the only thing that I need to put on the bottom. That's what all of this stuff means. If there are multiple letters that are repeating, that's where S2 and SK and all that comes in. So since E is the only thing repeating, we only need it E down here, and there's 2 E's. So 4 factorial is 4 times 3 times 2 times 1 over 2 factorial is 2 times 1. The 2's cancel, so we just get 4 times 3, which is 12. So there's 12 different ways that we could arrange the letters in the word even. Now let's try California. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters in the word California, but there are some repeats. Now let's see, I've got 2 A's, 1, 2. Oops. I need to plug my computer in. Looks like we have 2 I's. Is that all we have repeating? C-A-L-I. 2 A's, 2 I's. I think that's it. I'm gonna go crazy if I'm missing any. But at least I hope that's it. If I'm missing any, yell at me in class tomorrow. So this is going to be 10 factorial, which I'm just going to do this all on my calculator. 10 factorial is 10 times 9 times 8, and so 10 factorial is 3628800 over 2 factorial times 2 factorial. That's just going to be 2 times 1 times 2 times 1, which is just going to be 4. So I'm just going to divide that by 4, and I get 907,200. Oops, that's where the comma should be. All right, tomorrow we have a total of 1, 2, 3, 4, 5, 6, 7, 8 numbers, and we're going to divide by how many the factorial of how many we have repeating. So we have 1, 2, 3 O's, so 3 factorial. Then we have 2 R's, and that is it for our repeats. So this is going to be 8 factorial divided by 3 factorial divided by 2 factorial. So 8 factorial is 4,032,0. Divide that by 3 factorial, which is, so divide by 3, and then divide by 2, and then divide by 2 factorial, which is just another 2. So I got 3360 as an answer there. I'm going to have you guys try yesterday on